So as we have seen in the previous video, when we were setting up the material mixture template material properties, we have selected for thermal conductivity mass weight law. Okay, and just go back and show you over here. You can see mass weighted mixing law is what we have selected. Okay, now if you're not aware what is thermal conductivity, then try to just Google about it and try to understand what is it. Okay, because we cannot dive in to such basics, and that is not a big problem. If you really don't know, you can just find about it, because at any moment one have to understand all these things, right? The thermal conductivity must be defined when heat transfer is active. You will need to define thermal conductivity when you are modeling energy and viscous flow. Okay, so we have energy involved in our equations. Now ANSYS Fluent provides several options for definition of thermal conductivity. We can have some constant value for thermal conductivity, or we can have some laws which will help us, some theories, and some other different properties or different ways. Clear? Now the second one is very important for us, that is the composition dependent thermal conductivity. So I'll just go directly to that. That is 8.5.4. I will be attaching this notepad with the link. You can just press that link and you can just read if you really want it to be understood in a more better way. Now if you are modeling a flow that includes more than one chemical species, that is a multi-component flow, and that is what we are doing at this moment. So you have an option to define the composition dependent thermal conductivity, right? So what are we doing is we are defining thermal conductivity in the form of composition dependent strategy. Okay, so for composition dependent thermal conductivity for a mixture, we can go with mixing law, that is mass weighted mixing law or ideal gas mixing law, right? So I have seen few articles wherein they have gone with mass weighted mixing law, few articles have gone with this thing. So it depends on cases to cases, the kind of references what we have to consider that, and we can just proceed with that as well. So for that reason I have selected the mass weighted mixing law, and same goes for viscosity as well. Clear? So we must be very clear as to we must be very clear with respect to the reason for selecting different things or different options in ANSYS Fluent. I mean, that is what is all about. You can just select different options and get some colorful results, but do they really predict, or try to replicate a closer form of realistic simulation, realistic case? That is what is more crucial, right? So the selection of equations is very important when we solve any form of cases. It can be an aerofoil, or it can be this kind of case, or it can be an hydrodynamic case, or any oil and gas case, or whatever case you're doing. The selections of equations are more important, right? And yeah, so after this, what is the next task? Let me just minimize the models and materials. We are done with this thing. Now let me just go and select the boundary conditions and select the this option called as zone type. So this will group the boundary conditions based on the naming what we have given, right? Now the fresh air inlet is nothing but the complete open area of the shop or the garage, right? From where the from where the air is entering. Now as I have not considered the realistic dimensions, so I'm just going with very lower values of velocity as well. Okay, so I'm not just going with the realistic velocities. Let me just assume that the velocity in our case is 0.09, okay, closer to 0.1 meters per second. Okay, otherwise we'll just assume it as 0.1 meters per second. Clear? Then after that we will go to thermal, and let us just assume the wet temperature is 293 Kelvin. Okay, now apart from that, you can see that as we have turned on the species model, the species tab is active at this moment, isn't it? So here we need to define the species or the mass fractions of that species what we have. Okay, now you must be seeing that we have the water vapor, we have the oxygen over here, and we have carbon dioxide, but we don't have the nitrogen over here, right? So do not worry about it. What ANSYS is created in a way, I mean the Fluent solver is created in a way, for example, if we are defining the species of fresh air, that means we are just imagining that we have the oxygen in this particular oncoming air with a percentage of 0.23, okay, and we are just pressing apply, but we are not entering any value for nitrogen. Now after clicking apply, the software will automatically calculate the value of nitrogen. So what does it do is, whenever we are defining the mass fractions of n number of species, okay, for example we have 4 species over here, then if we are adding all the mass fractions, the sum must be equal to 1. That is the condition what we have, okay, you must be aware of this thing. The sum of species, the sum of mass fractions or mole fractions for species or a composition of materials must be composition of all the different materials. I'm just saying, okay, oxygen is a gas basically, but I'm just referring as material. So the sum of all the mass fractions must be equal to 1, right? Now as we have entered the species for oxygen, that is 0.23, so the software will assume on its own in the background 1 minus 0.23. 0.77 will be assigned for the nitrogen in the background, right? So this is how the software calculates. I mean, it is created in this way, so we have to understand and we have to deal in that way. We need not worry about it that there is no possibility for us to enter the nitrogen value, that is 0.77, and how can we represent it as an air. Don't worry about it, okay. We have the value of oxygen 0.23, that is well and good, and automatically the software will subtract 0.23 from 1 and you'll be having 0.77 in the background for nitrogen. Clear? Now I believe that we have set up the pressure, I mean we have set up the air inlet. Click on apply and close it. Clear? Now for the outlet, we can just leave it as pressure outlet, right? We can just leave it as pressure outlet and we can just leave the gauge pressure values. Now for thermal and species, I mean we can just leave it, because when the solution is happening, the values will be taken from the inlet and automatically at the outlet it will be predicted. I mean we will get the values after solving automatically at the outlet, but like during the solution process there may be some inflow through the boundary, through this boundary as well in the beginning. So for that case we will be defining the same values of species at the at the outlet as well, okay, especially with respect to temperature and 293, what was it, yeah, 293. So we will just define these two at least at the boundaries, okay, at the outlet boundary, and even if we are not defining it, well and good, no problem, it will automatically solve it. So we will just close it, and we are done with the outlet as well. Now what is the next thing? The next important thing is the fire source. So where is the fire source hidden? The fire is available over here. Now what kind of boundary do I need to assign for, boundary type do I need to assign for this fire source? Okay, now I cannot assign a velocity inlet for this, okay, because I will not know the velocity of gases which are coming out from the fire, okay. So in this kind of cases where species are involved, for most of the times it is really suitable for us to go with mass flow inlet, okay. So in mass flow inlet, the important thing what we have to enter is the mass flow, that is the amount of mass per second which is coming out from the boundary, and that will be in kgs per second. Clear? And the direction of that particular mass, I will be choosing it as normal to the boundaries. Just go to the direction and click on normal to the boundary. Now for realistic cases, your dimensions of the model will be in meters, say for example 7 meters or 6 meters wide, but I have just reduced it drastically. So I'll be going with a very smaller values, say for example 0.001 kg per meter second, kg per meter, I mean sorry, kg per second, really sorry. Now the gases which are coming out are extremely hot, so let us keep the temperature as 1200 kelvins. And the next important things is species, and for the species we will be entering the water vapor value, okay, and we will be providing the carbon dioxide which is coming out from the gases, sorry, 0.3, right? So I will be noting down these values, and we can select mole fractions over here, and now we will be entering the value of the carbon dioxide, that is equal to 0.35 and 0.65 here. So I have this particular window over here. One second. Mass flow inlet, I think I've opened. Yeah. So mass flow boundary conditions can be used in ANSYS Fluent to provide a prescribed mass flow rate distribution at the respected boundary or inlet. As with the velocity inlet, specifying the mass flux permits the total pressure to vary in response to the interior solution. This is in contrast to the pressure inlet boundary condition where the total pressure is fixed. So we can just see over here, the mass flow inlet is often used when it is more important to match a prescribed mass flow rate than to match the total pressure of the inflow stream, right? So we are trying to, we know the mass of gases which are coming out in kgs per second. So we will be just entering that particular thing or that particular value. Okay. Now, I'm just getting reminded of a paper which I have read. In that particular case, they were trying to replicate the amount of carbon dioxide what a human is emitting from his mouth. Okay, so they have created a kind of mannequin, and they have created a mouth surface. They have named it as mouth, and at the mouth they have assigned carbon dioxide species coming out from the mouth of the model. Okay, and in that case, they have mentioned that they have selected the mass flow inlet and they have assigned the respected values in kg per second. Okay, now as per some medical study, what they have written was the carbon dioxide which is coming out from us, that is from humans, is having a mass flow rate of 1e minus 6 kg per second. That is a very smaller value, but that is the rate of emitting of carbon dioxide from human. I'm not saying it on my own. I mean, it was written over there with the proper medical references, right? So in that cases also, mass flow inlet must be used rather than entering the velocity, right? So that is the reason I'm just going with mass flow inlet and entering the species of this carbon dioxide which is coming out, carbon dioxide and water vapor which are coming out from the fire, or the gases what are present, they have this composition. Clear? Now I'll just click on apply and close. Now you can see the fresh air inlet is automatically sent to the inlet zone, clear, or inlet group. Outlet is done. Now the car body will be aluminum body, we'll just leave it as it is. Okay, so we can just check up over here in the edit, go to thermal, and material name is aluminum, right? But for the ceiling, floor and wall, we will be changing the material as what? As concrete. So I'll just go to thermal and go to temperature. Let the temperature be 300. We will be assigning the material as concrete, and we will be turning on this shell conduction option. So this option will enable thin walls. I mean, if you have seen in the CAD software, this is a thin wall what we have created over here. This is the wall. Yeah, this wall is a thin wall basically. If I'm just showing you the cross section, this is a thin wall. It is not a solid like this model what we have created over here. Clear? So for if we are turning on the shell conduction, this option will enable thin walls to solve the heat transfer in the normal and planar directions without the need for having a thicker walls. So I'll just click on edit over here and enter the thickness of that wall to be something around 0.3. Clear? And we will just leave the material as concrete and leave the heat generation rate to 0. Click OK and click apply. So the ceiling is set with the boundary of concrete. Now I want the same conditions of floor and wall. So if you really want to save your time, you can just go to what do you call, copy option, and from copy option you can select ceiling, because I want the properties of ceiling or the data of ceiling to be copied into floor and wall, right? So I will be using this option, and after that I'll just click on copy. Now this will ask me copy ceiling boundary conditions to all the selected zones. I'll just click on OK, and it will load for a while and we can close. Now if I'm just going to floor, let me verify whether it is copied appropriately or no. You cannot totally rely on the software to work, you just have to verify. You can see temperature is selected, concrete is applied, 300 is written, shell conduction is done, edit thickness is done, concrete is assigned over here. So everything is copied. This is what is the simplest procedure to copy. Now we have only 3 boundaries. Imagine, in cases if you have many boundaries, like like 10 or 15 walls, like if we have seats, humans, or I mean human will not be a concrete obviously, but I'm just giving an example. So if you have a common conditions for all the walls or all the boundaries, you can just use the copy option, but randomly try to verify as well, because sometimes maybe you will not be selecting appropriately or we will not be selecting appropriate. Now I'll just pause the video. In the next video we will be discussing about operating conditions and we'll proceed with that.